Okay, so we are now recording this session. Okay, so the first type of topic is binary and hexadecimal systems. As we said, in order to be able to understand how Bitcoin, but not only Bitcoin, all fintech platforms, how they work, you need to be able to understand the binary and hexadecimal representation of numbers, okay? Because this is how things are done inside the computer. And because in fintech, financial technology related to money, things need to be very accurate, so you need to fully understand how are things exactly expressed within the computer system or within a computer network, so that you can understand the full accuracy of things. Because this is not, I mean, everything in Bitcoin or Ethereum or any other financial technology needs to be extremely well specified. There is no room for error. There is no room for gray area. Okay, so the first type of problems here is you may be asked to find binary representation of a number. So you are being given a number, in that particular case, let's say 123, and someone is asking you to find the binary representation for this number. How do we go about that? Well, in order to find binary representation, remember binary representation of a number means we need to basically write this number in powers of 2 effectively. So the first question you need to answer is what is the largest number of power of 2 that goes within 123? Remember powers of 2 are 2, 4, 8, 16, 32, 64, 128. Now, 128, which is 2 to the 7, clearly does not belong here. So you don't have any 2 to the 7th, but you will have the next one, which is 64, right? So 123, I'm going to write 123 in powers of 2. The first one will be 64 plus. Now, in order to find the next one, I need to subtract 64 from 123. So I'm going to my calculator and I subtract 123 minus 64, and that'll be 59. Okay, so let me do it analytically. So it's plus 59. Okay, then you have 64 plus, where 59, what is the largest power of 2 that you have there? It is 32, right? So I'm going to add the 32 plus, I'm going to take 32 out of the 59, so it's going to be another 27, plus 27. Then, uh, so I have a 64 plus a 32 plus, what is the next power of 2 that can go there? Well, the 16 is okay, right? 16 is smaller than 27, so you can have a 16 also. Plus, well, if you take 16 out of 27, there's another 11. So then you're going to have 64. Let me, 64 plus 32 plus 16 plus 11. Well, there is an 8 there, right? Plus 3. And then you're going to have 64 plus 32 plus 16 plus 8 plus 3, which is basically 2 plus 1. That's easy. Those are all powers of 2, right? So I have written basically 123 as a summation of powers of 2. So I just need to put these powers of 2 in a binary format, which is easy. I start with 64, then 32, then 16, then 8, then there is no 4. Okay, 4 is missing. So I put a 0 there. There's a 2 and there is a 1. Okay? So this is basically your representation of 123 as a binary number. And that is what you need to do to be able to do that in an exam or in other type of framework. Okay. The other type of problem is the opposite, which is basically instead of going from the decimal representation to the binary, to go from binary to decimal, which is what we're going to do next. So next problem is we need to go from 1100,111 to the decimal to find what number that is. So 1100,111. Okay. Now we go the opposite way, right? We are writing down those numbers as powers of 2, okay? So we can just count. This is 1, 2, 4, 8, 16, 32, 64. So the biggest number of there is 64, plus you have a 32 also, plus there is no 16 because there is a 0 there in the place of 16. There is no 8 because there is a 0 in place of 8. And then there's a 4 plus a 2 plus a 1. So if we add all these numbers together, that'll be like 96 plus 4, 103, if I haven't made any mistake. Okay? That's how we go from the binary to the decimal, to the number which is we as humans usually think about. The next type of problem is basically to find the hexadecimal representation of a number. So you're given 1, 2, 3 again, and you are asked to find the hexadecimal representation. Now, the first thing would be to do it in binary first, to go to find the hex representation. Uh, we first uh, write the number in binary format. Okay? Now, it so happens that 123, we have done it already. So we have done it in problem 1 above. So 123 we know is equal to 1111,011. Okay? So now I need to write that down as a hexadecimal. Well, as we said many times, once I'm in binary, it's very easy to go to hexadecimal. I'm jokingly say that those two systems are cousins because it's very easy to go from one to the other. How do we do it? We basically separate the binary number in groups of four, okay, going from right to the left. So if I come here, I'm going to write 111. 1011, and I put a space there so it's easier for our eyes to see basically the split in groups of four. Okay, now the problem, one may say, well, okay, I understand the number in the to the right, but I don't understand the number to the left. Hold on. I don't understand the number to the left. Well, yes, because it's a three-digit number, three binary digit, and usually we are used to translating four binary digits to its decimal, to its hexadecimal representation. But remember, I can always pad zeros to the left of a number, right? They don't have any value. I can pad as many zeros as I want to the left of a number. So that number I can write as 0, 1, 1, 1, and then 1, 0, 1, 1. Okay? And once I have done that, now I can immediately translate to the hexadecimal representation. The first digit is a 7, right? Because 0, 1, 1, 1, 4 plus 2 plus 1, that's a 7. And the second number is 8 plus 3, which is 11. And we know that the number 11 in hexadecimal format is B, right? Remember, A is your 10. Okay, so B is 11. So this is your hexadecimal format. Okay, as a matter of fact, to be very careful, we want to put a 0x in front to make sure that everybody understands that this is a hexadecimal number. It's a good practice to always put a 0x in front of a hexadecimal number. This is the convention also in Bitcoin and all financial technology is always hexadecimal numbers are always represented with a 0x in front. So we will do like that. The next type problem is basically to go from a hexadecimal to its decimal representation, right? I mean, previously, problem number three, we went from uh, the decimal representation to the hexadecimal. Now we want to do the opposite. We want to go from hexadecimal to decimal. Okay? So I'm writing the hexadecimal first. 1AE. Okay, so how am I going to do that? Well, remember that hexadecimal means that the number is basically written in powers of 16, right? Like decimal is powers of 10, hexadecimal is in powers of 16. So your first digit there, your 1, will be multiplied by 16 square. Your next letter is A. We know A is a 10, right? Is a 10 times what power of 16 will that be? That's going to be a 16 to the first, right? So it's just 16. We don't need to. 16 to the first power is equal to 16. And finally, there is an E. And an E I know is a 15, right? Sorry, it's a plus. 15 times 16 to the zeroth power, but we know 16 to the zeroth power, like any other number to the zeroth power, is equal to 1, so I don't need to write. So that's going to be equal to 1 times 16 squared, that's 256. That's the power of 2, that's why we know it. 10 times 16, that's 160, plus 15. And then I can use my calculator to add this 256 plus 160 plus 15. That's 431. So yeah, that's a 431. Okay? Is it clear so far? Any questions so far? Okay, everybody understands. So you should all do very well in the midterm. Okay, now we are asked to find a binary representation for the 0x, for the hexadecimal number 1AE. Okay, so of course one can do it by taking to binary 431, right? Because we know 1AE hexadecimal is equal to 431 decimal, but this is probably not the smartest way of doing it. Here, what we remember is basically hexadecimal is the cousin of binary. So you can go back and forth from hexadecimal to binary very easy without need of any calculation. Okay, how do you do that? Well, 0x 1AE is equal to, I just take one digit at a time and translate it to its four binary group. So 1 is equal to 0001. Your A, which is 10, you just need to write 10 as a four binary digit, which is basically 8 plus 2. That's your 10. And E, which is 15, which is basically 8 plus 4 plus 2 plus 1. That's the biggest number you can represent as a binary four digit. Okay? And you can also put it all together if you want to by just dropping out the three zeros to the left and merging all strings together. So it's going to be 1, 1, 0, 1, 0, 1, 1, 1, 1. Okay? If you want to look at it like that, even though I don't necessarily, I wouldn't basically suggest that because it's actually better to look at numbers always in groups of four. But anyway, it's okay. Whatever it feels better. Okay? And the final type of problem is to find a hex representation for a relatively large number. Let me copy paste here so I don't make mistake because it's easy. You see, it's very easy for humans to make mistakes when they try to deal with binary numbers, large binary numbers. It's extremely difficult. So it's not natural for our eyes, for human eye, to deal with large binary numbers. So that's why we are using hexadecimal numbers basically. Otherwise, we would always be making mistakes. So how do I find hex representation for that? Well, again, I just write in groups of four, starting from the right, moving to the left. And this one you can also write okay, like that. I put an extra zero so that they all look like four binary digit numbers and we don't get confused. And now I can immediately translate to hexadecimal. I put my 0x in front as always to designate the fact that I'm dealing with a hexadecimal number. And then I translate my groups of four into their hexadecimal digits. The first one will be a 4, right? How about the next one? Actually, I have a mistake. I just realized I made a mistake here. Uh, Phew, okay, it's only up to here. So let me, this is, E is not 15, it's actually 14. So that's a 14 here. That's a 430. Sorry about that. Okay, so an E is a 14, right? So uh, if I want to write 0x1AE from hexadecimal to find what number that is, I'm going to start with 1 times 16 square plus 10, which is A, times 16 plus E, which is 14, not 15, but 14. 15 is an F. Okay, so that when you add all these numbers together, that'll give you a 430. And then if you want to go to the binary representation from 0 for hexadecimal 1AE, E is actually 14. So again, we work one digit at a time. 1 is equal to 0001. I can always put extra zeros there. A is 10, so 8 plus 2 is 10. That's the representation of 10. And E is 14, which is this one. So like that. Okay, so that's my binary representation for the hexadecimal 1AE. Okay, finally, a must to find the hexadecimal representation for this long number here. I just need to break it down to groups of four. But remember, groups of four going always from right to left, not from left to right. That would be a mistake. So you cannot start from here and break like that. That'll be a mistake. Okay, so you start from right, okay, going to the left, from the least significant to the most significant. So once I have them in groups of four, then my 0100 is a 4. The other number is your 14 basically because it's 8 plus 4 plus 2 and 14 is an E and the final number is an 8. So that binary number is a hexadecimal 4E8. Do we have any questions?
No, sir.
Okay, so everybody should have understood well by now how these things are done. And therefore, we can now go to the next type topic, which is solve problems related to Bitcoin mining mathematics. Okay, simple Bitcoin mining mathematics, effectively probabilities, I should say. Maybe I should call it probabilities, right? Bitcoin mining probabilities. Okay, so remember that the basic operation of Bitcoin protocol is that miners are asked to utilize hash function, cryptographic hash, with a nonce and keep on trying various nonce values. Remember, nonce is this arbitrary number that goes at the end of a block, trying to make the block hash into a specific hash value. As a matter of fact, below a specific hash value. So let us again let us go slowly for the last time before the midterm over the operation of Bitcoin mining. Okay, because sometimes you will see that the miners are solving a very difficult problem, something like that. This doesn't really truly convey the message. It's not, they don't really solve the problem. What they are doing is they keep on trying hash inputs, different hash inputs, until they get a hash output which is as a value below a specific target value. Okay? So, in order to do that, they need to be able to keep on trying new values, new inputs. But remember, the input that goes inside the hash is kind of given. It's basically the various transactions that need to go into the hash. Okay, and all Bitcoin miners will more or less utilize same set of functions, say, transactions. So how are they going to get the differentiation? How are you going to try various values until you get a winning hash? Well, the way you do it is by putting at the end of the block one more string which doesn't have any real value, but only to create arbitrary new inputs for the hash function until the hash output goes below a certain target value. Okay, that's the only reason you need this nonce is basically it allows you to keep on trying new inputs into your cryptographic hash. Okay, it's a 32-bit number that you keep on trying, changing until you get the right type of hash output. And when I say the right type, I mean the hash output with enough zeros at the left, or if you want to think about it better, a hash output that has a value less than a particular target value. That's your goal, basically. That's Bitcoin mining. There is nothing else to it. Okay? Uh, so it's not that you're solving a mathematical problem that they say or something like that. What you do really is a brute force approach. You keep on scratching new numbers as fast as possible, hoping that you'll be the first one to find the lucky combination. Okay, and that is why if you start looking around for Bitcoin mining hardware, you'll see that the basic, excuse me, the basic property of Bitcoin mining hardware is its hash rate, meaning how fast it can hash new values. For historical reasons, let's say that in the beginning, hash used to be done via general purpose computers like your laptop, but the crypto mining community, Bitcoin mining community, very fast realized they don't really need a general purpose computer to just mine. As a matter of fact, some people actually parallel say that this is similar to, uh, you know, effectively, what can I say? I mean, using a cannon to kill a mosquito or something. Basically, you're using a very general purpose computer that costs a lot, burns a lot of electricity, and can do all kinds of things. But in reality, the only thing you want to do is just keep on hashing, keep on doing hash computations, nothing else. So the Bitcoin mining community very fast realized there is a special type of computing machinery, which is called ASIC, and this computing machinery can give you extremely high hash rate uh, because it's very specialized. Basically, it's a very special purpose type computer. Okay, today you can spend around $1,500 US dollars, 1,500, and buy an inexpensive ASIC that's going to give you uh, maybe around, uh, well, I'm not so sure about the number of terahash, maybe 90 terahash. If my memory serves me right, you'll get something like 90 terahash per second, or let's say 100 terahash per second with a $1,500 machine. So it's basically you're going to spend the money that you would buy just a relatively good desktop computer that would give you a very small hash rate. But now you're going to get a hash rate in the range of 100 terahash. Terahash is basically uh, uh, quite large number basically. So it'll give you some probability of getting the lucky combination. Or if you belong in a Bitcoin mining pool, you have a probability of actually getting some real income, provided that your electricity is not very expensive, of course, because this is a critical part. Is what is the cost of electricity that goes into Bitcoin mining? I mean, Bitcoin mining effectively the biggest expense besides the initial capital outlay to buy the machine. The other one, the biggest expense is the electricity that goes into it. Okay. So anyway, the now so going back now to the mining, so the critical question is, what are the probabilities of getting this lucky hash? Okay, to finding the next arbitrary nodes that will produce uh, a crypto hash that has a value lower than target. So we need to understand this type of question basically. Okay, and this in this area you can we can play with various type of questions. So for example, here exercise number one, we are asked to find how many tries we would expect if we are asked to get a hash that starts with, remember the hash is always going to be a hexadecimal number. So 0x here means hexadecimal, but then we want it to start with a 0. So what is the probability of getting a 0?
Sir, there should be a 50% chance of getting a zero.
What is the chance again?
A 50% chance, 0.5.
0.5. Okay, be careful. This is not a binary 0. This is a hexadecimal 0.
Sir, will it be 2 power 10?
Say again?
2 power 10.
2 to the power of 10. Well, why 2 to the power of 10?
Sorry, 2 to the power for I thought it was question 2 to the for two zeros, it would be 2 to the power of 14.
2 to the power of
14
14.
because the hash function is has a
Okay.
16 numbers long.
Okay, be careful here. This 0x here, the beginning 0x, is not part of the number. It's just a way to a convention to tell us that this is going to be a hexadecimal number. So we want to
Okay.
have a hexadecimal that starts with a 0. So it's a hexadecimal which is going to be like 0x, which means hexadecimal, 0 DDD something.
Okay.
That's the number you want. So what is the
Mm.
probability for that?
2 power 15, I'd say.
2 power 15.
Yes. I'm not sure.
Okay,
So
let
it will
us
be 1 divided by 16.
1 divided by 16, right? That's correct. Okay, because remember, you have a single hex 0, which means, let's put it like that. Sorry. A single hex 0, a single hex 0 in the beginning, which means 4 0 bits. So the probability is 1 divided by 2, which is 1 0 bit, and all of that to the fourth power, right? So if you divide 1 by 2 to the fourth, 2 to the fourth is 16. So it's 1 divided by 16. And if we want to think about it, the exact number is 16, 1 divided by 16. That's 6.25% or 0.625 or 6.25%. That's your probability of getting a hexadecimal number that starts with a 0 hex digit. Be careful, this is a 0, it's a hex digit, not a binary digit. Okay? Is everybody okay with that now?
Yes, sir.
Okay. Okay, good. So let us now go to the next problem. The next problem wants to ask us how many times we expect to try in order to start with at least 6, be careful now, 6 0 bits. Remember, a bit is a binary digit, right? A bit is a binary digit. That's what a bit is. Okay? It's not the same as a hex digit. Okay? Not the same. Okay, I don't have the symbol, so let us, maybe I have it actually. Let's see. Okay, I cannot find this symbol, so that's fine. It's okay. Binary digit, not hex digit. As a matter of fact, hex digit is equal to 4 bits. Okay? Please remember this. So don't confuse a 0 hex with a 0 bit. So here we are given we are asked to find the probability to get at least 6 0 bits. What is the probability for that? Remember, for a 0 bit, I have probability 50%. To get 6 0 bits in a row, I need 1 over 2 to the 6th power. And this is equal to 1 divided by 64, right? So that's a much smaller probability. Let's go to our calculator. That's 1 point or equal to 1.5625%. Okay. So the probability of 4 zeros was 625, probability of 1 zero, 6 zeros, 6 bits, sorry, 6 zeros is 1/4 of that basically, which is 1.5625. By the way, what if someone asks, no, that's okay. Let's see. What if someone asks, let me solve that. This is interesting actually. What is the probability to start with? Let's, instead of giving us at least 6 0 bits, to start with 0 1 1 1 0 1. So now we are given a specific 0 sequence, so a specific binary sequence of 6 digits, specific bits, 0 1 1 1 0 1. What is the probability of that? Is it the same as the probability of 6 0 bits or different? So that'll be two problem. Okay, so actually it's the same. Okay. Doesn't matter what exactly is the sequence. All that matters is that we want to specify a specific number for specific 6-bit sequence. Is the same. It doesn't matter if we want it to be zeros or we want it to be zeros and ones or whatever. As long as we specify a particular binary digit sequence, a specific 6-bit sequence, the probability of getting it is 1 to the 2 to the 6, 1 divided by 64. Is that clear? Because for every one of those, you need 50%. Like to get the first zero, you need 50%. To get the next one, which is a one, you again need the 50%. To get the next one, which is a one, you need 50%, 50%. Each time you specify a particular outcome, you multiply by 50%. Now, let us come here. A little more difficult type of problem is that we are asked not a particular sequence, but we are asked to get a number which has a specific number of zeros, and we are asked what type of numbers, what type of hexadecimal numbers would satisfy that. So in that particular case, we are asked, we want to have 50 bits. And the question is, what are the hex numbers? Because remember, the output of the hash function, when we look at it, is basically a hex. And we may want to be able to recognize numbers with at least 50 bits. But instead of looking at them in a binary format, we look at them on the hexadecimal format. So we are being given hexadecimal numbers, and we are asked what are the hexadecimal numbers that start with 50 bits if converted to binary. Okay, let me say that again. We start with hexadecimal number and we are asked what are these numbers what are the hexadecimal representations that have the property of starting with at least 50 bits. Well, in order to solve this problem, we need to start thinking about it. Okay, numbers that start with at least 50 bits means what? It means that you're going to start with something like 0000, and then remember, I'm breaking it down to groups of 4 so I can understand what's happening to the hexadecimal representation. So then I'm going to have 0, and then I'm going to have something else, which could be like, let's say, y, y, y. I don't know what these numbers will be. Okay, and then something else. So what are these numbers? Well, the first hexadecimal will be 0. The first hexadecimal will be 0 because you have 40 bits. But the second hexadecimal will be some number that starts with a single 0. Now, what are the hexadecimal digits? Excuse me, that start with a 0 to the left. The hexadecimal digits that start with a 0 to the left will be any number, like for example 0. Is 0 hexadecimal 0? Does it start with a 0 to the left? The answer is yes, right? If I have a 0 hexadecimal, that's 4 zeros, 4 binary zeros. So that's going to start with a 0 to the left. How about, let's do it here. A 0 hex is equal to 0000. A 1 hex is 0001. So that's also starting with a 0 to the left. A 2 hex starts with 0010. So that's okay. And so on and so forth. Then I'm getting to a 7x, 7 hexadecimal. That's a 0111. And that's your last, the biggest number that has a 0 for the first binary digit, because there's the 8. If I take the 8 hexadecimal, that is 1000. So if you get an 8 and above, and so on, okay? So if you get an 8 and above, you're not going to have a 1 at the leftmost bit. So the only numbers that have the property of starting with a 0 bit are numbers 0 to 7. So your hexadecimal needs to start with a 0. The first hex digit will be a 0. That's your first 4 bits. And the second digit, let's call it a Y, will be Y needs to be less than 8. Any hex number which is less than 8 will do it. So if I start with 03, for example, yes, 03 has at least 5 0 bits. If I give you 07, yes, that starts with at least 5 0 bits. But if I give you 0A, for example, then it doesn't have 5 0 bits, it has only 4 0 bits, and so on. Is it clear? Okay, so if there is no other questions on this one, then we can also move on to the next topic, which is related to Bitcoin mining difficulty. Okay, so here we need to understand how by changing the target value or the difficulty of a Bitcoin mining, we can get various types of Bitcoin discoveries. So we want the Bitcoin discovery rate to have a specific value. For example, we know that in Bitcoin case, we want to have a discovery, a block discovery, approximately every 10 minutes on the average, right? But this 10 minutes is not a magical number. It could be some other coin. You could have different type of expectations. So maybe you would like to have a discovery every 3 minutes or every 7 minutes or every 20 minutes. Okay, so all kinds of various combinations can happen. So what we need to remember is that the discovery rate, the block mining rate, depends on two parameters, on two things. First of all, it depends, of course, on the difficulty, how difficult it is to find a block, but it also depends on a hash rate or computing power that goes into Bitcoin mining. The higher Bitcoin mining computing power, the faster we will find the next Bitcoin. Okay, so the main equation that you need to remember here is that the expected Bitcoin, uh, Bitcoin, sorry, mining rate, Bitcoin mining delay, let's say, or I should say, expected block mining delay is equal to the difficulty divided by hash rate. That's the equation you need to remember. So the higher difficulty, the more delay we expect to have until we find the next block. The higher hash rate, the smaller delay we expect. Makes sense, right? If I throw a lot of hash rate in Bitcoin mining, I'm going to get the next block faster. So the hash rate goes in the denominator. So this is the basic equation we need to remember so we can solve problems here. So let us try to solve uh, problems. And in particular, the problem here is we have a world with very slow computers and we mine a coin, we call it slow coin, that only uses 20-bit hash for proof of work mining. Okay? Now remember, 20 bits is basically 4 times 5, 5 times 4, right? So it's 5 hexadecimal digits. Okay? So let us try to start. We will not finish this problem today. We will continue next Thursday, but let us start it. So the total hash space, total space of 20 bits is equal to 5 hex digits. Okay? And we are asked to figure out the total space of hash values, of hash output, let's say, actually. Okay? Well, that's kind of easy, right? This is the total space, total output space is equal to 2 to the 20th. Which, if you remember, the first thing you need to do to put it in terms of 2 to the 10, because that's the one we know, 2 to the 10, and this whole thing square, which is basically 1024. Remember, 2 to the 10 is approximately 1,000, right? It's actually 1024 times 1024. So it's approximately a million. As a matter of fact, to make it more specific, it's going to be 1024, sorry, 1024 square. I'm using my calculator here. 1 million 48. Okay, that's your number. That's a power of 2 also. It's 2 to the 20. This is what we call 1 mega, by the way. That's 1 mega. Okay? Remember, what 2 to the 10 is 1 kilo, 2 to the 20, 1 mega, 2 to the 30, 1 giga. Okay? 2 to the 40, 1 tera. Okay, so that's your total output space, approximately 1 million outputs. Okay, so now we want to mine a block, a slow coin. We want to mine a slow coin block, and we want a hash that starts with 00 when we are asked to find a difficulty. Remember, the difficulty what is the definition of difficulty? Well, there is two definitions of difficulty, okay? One definition of difficulty is the number of expected tries before I get a winning hash. So difficulty is expected hash tries per block. How many times am I expected to hash before I get a winning hash? A block. A block is a winning hash. So difficulty 20 means I need to try 20 times before I get my next block. On the average, remember, it's always talking about the average. So when I say 20, it may come to 25 or 15 or 40. Okay, we're always talking about the average. So the average number of trial hashes per block, that's your difficulty. Another way of thinking about difficulty is think about the total output space divided by target space. How much bigger is my total output space when compared with the target space? Target space, which is much smaller, right? Because remember, target, I need to get below the target to get a winning hash. So if I divide the total output space by the target space, that's going to give me the difficulty also. It's the same number. So use any one of those two, regardless of the one that makes better for you, makes more sense to you. Okay? So let me separate the two so that you see that they are two different types of ways. Okay? Uh, and finally, also, difficulty is interestingly one divided by the probability of a winning hash. So if I define by p, the probability of a winning hash bp, then the difficulty is 1 over p. Another way of calling the probability of a winning hash is the number of blocks that you're going to get per hash, right? How many blocks do you expect to get per hash? Of course, you're going to get a much smaller than one, right? Now, all of those definitions are equivalent. I'm just putting them all together here so that it helps you during midterm and it helps you basically understand the concept. And sometimes some people prefer one definition than the other. Regardless, I put them all here so that it helps you understand and visualize. Now, in order to answer the question here, number two is we want to find difficulty in a situation where we need to get a hash which is starts with two zeros. Okay, well, if a hash starts with two zeros, let me copy here. Okay, for a hash to start with like that with two zero hexadecimals, the probability of winning hash is what? We did that already previously. Remember, two hex 0 digits means how many binary digits? Every hex 0 is 4 binary zeros. So to get two hex zeros, you need 8 binary zeros. So probability is 1 divided by 2 to the power of 8. And that is 1 divided by 256. That's your probability of a winning hash. So if this is your P, therefore, from P equal to 1 divided by 256, we can figure out the difficulty is equal to
1 divided by 256.
1 divided by P, right?
Yes. Yes.
Well, if P is 1 divided by 256, how much is 1 divided by P? The inverse of P, which is 256. Make sense, everybody?
Yes.
Okay, so once I find the probability, it's very easy to go from probability to difficulty. Okay, so the difficulty is 256. That means that your output space is 256 times bigger than your target space. Okay, so we will continue the idea probability the next time because this is critical for answering questions. I don't want to do all of them today because, first of all, we are running out of time, but it's also quite critical. I want you to think a little bit about these things before we go to the next preparatory meeting for the midterm. For those of you who came late, let me just say again that the midterm will most probably be full multiple choice. There is a possibility of a single question which is not multiple choice. I'm still thinking about it. I haven't finalized midterm yet. But the biggest part of the midterm, the most points will come from multiple choice type question. And the problems will be related to what we're doing today and what we will be doing on Thursday also. So by studying these things, you should be doing very well. I will erase all of these things, by the way, back to the LMS. So these things I will put the things we did now to the LMS so you can study. Okay. Uh, and that's about it basically. So this is how it's going to go. As I said, there's not going to be any surprises. Midterms are usually things that we discussed in class. So those are the things you should expect to see in the midterm, and those are the things you should expect to know how to deal with to do very well in the midterm. And we will continue this discussion related to the midterm preparation on Thursday. Do you have any questions?